Hello, coming here for another video of relation and function, right? So we'll be starting with the rest of the parts. Today, first of all, I am going to discuss a very important point, very important point, which we always have something called transitive relation and trivially transitive, right? Two questions first we will be discussing, two topic, and then we'll be discussing the questions. So first of all, just I would like to remind you about transitive relation, right? Transitive relation, transitive relation. So already you have studied this. So if I tell you about the definition, so there will be no problem at all. So I will not write very clearly these things. Already we discussed. Just I am writing the criteria. That if AB belongs to R, BC belongs to R, and that implies A comma C is also belonging to R, for all ABC taken from that set A, then we call it a transitive relation, right? This is the criteria by which we observe, right, or we decide whether the relation is transitive or not. Now sometimes what will happen, let me try to talk about that also. First of all, if you observe AB and BC both are there in the relation R, and then you also find AC belongs to R, then we can complete the statement that this is a transitive relation. But sometimes in case of some relations, what you will find that AB is there, BC is there, but AC is not there, then it is not transitive. I am picking up one example, then it will be easier for us to identify the question. So for example, where I'll take one where it is not possible to find AC, right? For example, if I consider the set A as set of all lines, straight lines, of course I must fix it, straight lines in a given plane, right, in a given plane, and R is the relation where line 1 and line 2 will be related by the relation of perpendicularity, right? So if this is the relation, now let us just try to see what happens. Okay, what happens is that first we can find two lines which are perpendicular to each other. It is possible, right? Similarly, suppose this is L1 and we have found another line L2 and these are perpendicular. I can find it. Similarly, I can find in the same plane one third line L3 which is perpendicular to L2. This is also possible, right? But in that case, do we have L1 perpendicular to L3? No. Simple geometry always tells us that L1 must be parallel to L3. That is, L1 is not perpendicular to L3, which implies that L1 comma L3 does not belong to R, right? So what will be our conclusion? R is not transitive. R is not transitive. So here I have picked up one example. Here I have picked up one example where we have A comma B belongs to R, B comma C belongs to R, but AC does not belong to R. In this case, very clearly we can say that the relation is not transitive. There is no doubt about that, right? Or in case we could have got A comma C also belonging to R, then undoubtedly this relation would have been transitive. Now let us pick two situations which are little different from the case what we discussed. right? So let's move on to that situation. So situation 1. I'm writing situation 1. What may be the situations? I'll be citing you the examples so that you'll be at comfort, so that you will easily understand the concept without any kind of problem, right? So situation 1 will be something like this, that A comma B will be possible, right? It will be found in the relation, and B comma C, this part will not be visible. It will not be visible, right, in R when we write in the roster form. Let me try to tell you, I am saying not visible. I am not saying that this does not exist, right? It will not be there, I am not saying. I am only saying that it is not visible, right? Try to understand that particular sense. I am going to pick up one example. So if you will not be able to find any such ordered pair is not visible, right, then we call that this particular relation is trivially transitive. Now I'll be going for detailed explanation because this is little controversial topic. Many of the persons says that this particular situation doesn't give us to trivially transitive relation, rather that will give us to non-transitive relation, right? So I'll be picking up now one example that is taken from the book only, so that I'll be making it more clear, right? I refer directly to exercise 1.1, right? Question number 1, and it is part 2, right? Here they have given you this relation and they are asking you to check all this, whether it is transitive, reflexive or symmetric or whatsoever, right? So these are the conditions given. So now we have to check whether it is transitive, then symmetric, reflexive or not, right? All the three criteria we have to justify, or we have to check one by one. Let us start with, to make it clear, by writing this in the roster form. It is better for us, then we'll be able to observe it very clearly. I am allowed to take, here I did not write one thing, x is belonging to natural number. So I can start with 1, that is the possible value which I can allow, the lowest possible value. So it will be 6. Very nice. I can apply 2 because 2 is less than 4, so that will be 7. And I can apply 3, then that will be 8. So 4 is not allowed because it is strictly less than 4. So in the roster form we have only these 3 pairs. Now number 1, if I justify number A, reflexivity is not very clearly possible because 1, 1, 2, 2, 3, 3 are not there. So directly you can say, right, clearly it is not reflexive. As simply you write the counter examples, right? You may not write the general form here to show that it is not true, right? They do not belong to R. Number 2, is that symmetric? No, that is not symmetric as well, because 1, 6 is there, but 6, 1 is not there. So it is not symmetric also, right? As we'll write the example, 1, 6 belongs to R, but 6, 1 does not belong to R, right? In fact, if you want to impose the general structure, that also you can do, which implies that I'm making it little more explicit or explanatory, right? Which implies that, what does it imply? A comma B belongs to R does not imply B comma A belongs to R for all AB belonging to set A. Set A means here it will be natural number, better right, natural number. Okay, so till here there is no doubt absolutely. Now the real doubt comes here. Now you see, once we need to talk about the transitivity, we should start with a pair, say 1,6 belonging to R. What should be the next pair if I need to show? It should be starting with 6. Now can you find a ordered pair here which is starting with 6? No, it is not here very clearly. That means it is not possible for us to find one ordered pair starting with 6. Right? So here, does it mean that this relation is not transitive? People might say, okay, it is not transitive because we cannot show this particular implications. A comma B belongs to R, B comma C belongs to R, but A comma C doesn't belong to R. Right? But try to see. What is the other point or other side of visualizing this? This is what will imply this is trivially transitive. Let us think the observation in a different way. Can you say very definitely that 6 comma something would never be existing? Under this restriction that will not be here. But can you say that that will never exist, like 6 comma 11 say will never exist? Nowhere it will exist. It will exist. It is different case that because of this restriction we will not have it here. But I am sure that this kind of ordered pair can be there, which I am unable to find it here. So I am unable to carry on the process of proving the transitivity or disproving the transitivity. So in this case, I am unable to give also a counter example to say that it is not transitive. Try to understand the meaning. So if I do not have enough evidence to show that it is not transitive, then we have to accept it to be trivially transitive. I'll give more example for this again. First, let me write this particular statement. So what will write? This belongs to R, but we cannot find any ordered pair of the form 6 comma say some y I'll write in R, right? Okay, therefore this relation is trivially transitive. We are unable to show that it is not transitive, right? Now I'll be giving you a counter example just to support this particular logic. Listen to it very carefully, right? Listen to it very carefully and try to support this answer with the help of that logic. I'll do some sort of workout here. Not a very important workout, just see. Suppose you know that there is a person who is a thief, right? Who is a thief? There is a person, you know that he has stolen something from you. He is a thief, you know that. And when you found that he has stolen something, you have gone to the court, like legal action, and the case is registered in the court, and then now judgment is going on. During the judgment, obviously, to convict him as a thief, you need enough evidence. You all know that he has really stolen the things. But when in the judgment day or arguments day, you are unable to provide enough number of evidence which shows that he is a thief, then what will happen? Legally, he will not be convicted as a thief and he will be declared as innocent. Try to understand the situation. You all know that he is a thief, but you do not have enough evidence to prove that he is a thief, so legally he is not a thief. This situation is also like this. 1,6 is there, but you do not have now any ordered pair B, C type, right? A, B is there, but B, C type ordered pair is not there, which will support your argument that AB belongs to R, BC belongs to R, implies that AC does not belong to R, or does not imply that AC belongs to R. Do you have any such argument here? Can you find any ordered pair BC which will say that this will imply this? No, you cannot. So we have to, if we do not like also, we have to accept this as transitive. And that is the case where we use the word trivially transitive. The thief has been declared innocent, right? That's the explanation what I felt to be the best, right? So move on to the next situation as well. We now discuss situation 2. What other situation may be possible? Situation 2, right? I'm again going to discuss this problem with the help of questions from textbook only. So situation 2 will be what? A, B will be belonging to R and this will not belong to R. Now you try to make a difference with the previous one. Previous cases says that this can be there somewhere, may not be in R. But in this situation, this will never be anywhere. Forget about in R, even beyond the relation or beyond the set R, you will not find this. That means this doesn't exist only anywhere. So if this is the case, then it will be not transitive. Please make a sure note about this. That is the difference. So I'm going to pick up a question from the book only, because that type of question is there already in the book. So you'll be able to refer this question very clearly. That is, I'm giving you, it is from the same exercise 1.1, question number 1, part 5, and after that part 5 there is a part D. Relation I am writing R. X, Y, where X is wife of Y. Okay, I'll discuss all the 3 situations, and transitivity I'll discuss in little extensive way. Number, say what number I'll use. All these Roman and letters are used, so let me use a symbol star. Say star. Clearly X, X does not belong to R, as X cannot be wife of Y. Sorry, wife of X. Can X be wife of himself or herself? No. So it is very clear. Next, star dash. If X, Y belongs to R, you have started with this. What does it imply? X is wife of Y. Now, will it imply Y is wife of X? Apply the common sense. It will not be. So, if this is not the case, you can easily say that this is also not belonging to R. So here again see, there is a contradiction always. Many of you will write like this. No, I am getting this statement from these implications. So overall, if you start from here, now overall implication will be something like this, that this does not imply y comma x belongs to R. So it is not symmetric as well. It is not symmetric as well. Okay, now you come to the most controversial part. Will this relation be transitive or it is trivially transitive? Just let us try to explore. X comma y belongs to R. That means this will imply what? X is wife of y. Can I get ordered pair like this? What that implies? Y is wife of Z. Now just try to understand the complete explanation of this with reference to the previous also. I have to refer to the previous. In earlier case, we had no ordered pair starting with 6 here, right? But we could not guarantee that ordered pair starting with 6 will never be found anywhere in the field of maths. But here, this will never be found. This does not exist. If you go beyond R also, forget about R, you look for the general cases, you will never get this particular ordered pair. Why? Because if X is wife of Y, normal situation says that Y is a male, so male cannot be wife of another Y, right? So this is never possible. This is never possible, which is never possible, right? Which is never possible. So we do not have ordered pair only. So in this case, there is no question of discussing X comma Z belonging to R, which is not possible. So X comma Z belonging to R discussion is invalid, right? Because this will stop you. If you go beyond R also, you will never find it. But in the earlier case, if you go beyond R, you may have a chance to find them, right? So therefore, R is not transitive. So please find the difference between both the situations and try to tackle the other problems. This is just to discuss about this controversial matter of transitivity. We will get into the next video with the question answers of the respective exercises of this particular chapter. Thank you so much.